Inference for several proportions. So here we move from two proportions, inference on two proportions, to inference on several proportions. And when we do that, we have a different kind of sampling scheme. We have what's called a multinomial experiment. And let me see if I can motivate that for you on a few pages down here. So I think this is page 9 here. But suppose that at one time M&M Mars Incorporated, according to their website or whatever their publication was, they stated that the proportion of colors of M&M candies is as follows. And so that 13% of all M&Ms are brown, 14% of all M&Ms are yellow, and so forth. Now, I want us to think we ultimately want to test something about these percentages, but in the data that we're going to imagine that we would collect here, if we were in a face-to-face setting, we could actually collect the data. But if you imagine you had a large bag of M&Ms and you randomly selected an M&M out of that bag and you observed the color, you could see brown, you could see yellow, you could see red, blue, you could see orange or green. And so the outcome is not just binary, but now it has there's 6 possible outcomes. And so we call this a multinomial experiment. All right, so I want us to motivate that, and then we can talk about underlying proportions for each of the outcomes. So I can talk about the proportion of brown M&Ms, the population proportion of yellow M&Ms, and red M&Ms, and so forth. So with a little motivation there, let's come back to this beginning here of the multinomial experiment. Just to be clear, the properties of the multinomial experiment are as follows: that there are n identical trials, that each trial results in one of k outcomes. So the k for the M&M example would be 6 there. There's 6 possible colors, and if you force yourself to randomly select, say, 20 M&Ms, then that would be the number of trials there. Okay. Now the probability that a single trial will result in outcome I is given by pi sub I, and that remains constant from trial to trial. Okay, and the probabilities must also satisfy that the sum of all the probabilities is 1, and that's very intuitive here. So instead of having a single probability of success, what we have here is a probability of seeing the ith outcome, and we're going to have k of those probabilities. We also assume that the trials are independent, and that what we're interested in is the number of trials for the ith outcome, and so we're interested in observing n sub I. That's the notation we're using here, n sub I, for our sample here. So capital N is the overall sample size. N1 would be the number of outcomes that correspond, or the number of occurrences of outcome 1. N3 would be the number of occurrences corresponding to outcome 3, and so forth. And when you think about it, the sum of each of those outcomes has got to be the total sample size. Okay, so if we have a multinomial experiment, that gives rise to a multinomial distribution. This probability distribution is called the multinomial distribution, and probabilities for it are given in this expression here. The probability that I would see N1 outcomes for category 1, N2 outcomes for category 2, and so forth up to NK outcomes for category K. The probabilities are given by this expression here, and really this is a generalization of the binomial probability function, where in the binomial setting we just have basically an N1 and N2, and we can write everything in terms of number of successes, and you would actually, if you re-represented this formula in that way, you would see that this formula here is just a generalization of the binomial distribution. We're going to call pi 1, pi 2 up to pi k cell probabilities, and of course they correspond to each of the k outcomes. And we have observed cell counts n1, n2 up to nk. Now the expected number of outcomes of type I out of n trials is simply the number of trials times the probability of seeing the ith outcome there. Okay, so I have this note here on test statistic. I really want to kind of get through that. This is more or less out of place in terms of the note, so let's skip it for now. But this is we'll reference this. This is I will want to reference. This is typically called the Pearson chi-square statistic. What we can do with this distribution is test a particular hypothesis. And so I want to go back to this example with the M&Ms. I want to motivate this a little bit here. If you think about it, there's 6 parameters of interest, and so I'm going to flesh that out a little bit, that we have 6 parameters of interest. Okay, pi 1, which would be the proportion of all M&Ms that are brown. Okay, then pi 2 will be the proportion of all M&Ms that are yellow. And then we could have that designation all the way down to pi 6, which is the proportion of all M&Ms that are green. Okay, so I have 6 parameters there, 6 parameters of interest. And if I look at the question here, we're asking a question about the stated proportions of color there. Okay, so we're going to use ultimately sample data to test the hypothesis that the cell probabilities associated with the M&M candy's color distribution are not as indicated by the manufacturer. And so these are the we would say the null hypothesized values, or the hypothesized values of those population proportions. And so if we're solving this problem here in step 2, the hypotheses would be as follows: H0 and of course HA. H0 would be that pi 1 is equal to, what does it say here? The publication might say that pi 1, or would say that pi 1 is 0.13. And that pi 2 is, the proportion of yellow is 14%. Okay, that pi 2 is 0.14. And all the way up to pi 6 is equal to 0.16. Okay, and so if you can imagine, this was perhaps stated, if this was stated on their website or on some publication, we could test these color proportions as they're set here. That would be the null hypothesis. The alternative would be that at least one is not true. That is, at least one of the population proportions is not specified as under the null hypothesis. Okay, so do we have evidence to refute this percentage distribution designation there? That's what we're after. Okay, so we're doing inference on several proportions here. This is a particular kind of inference in this scheme. We're testing the goodness of fit for several proportions. Okay, so this test, what it allows us to do is this chi-square goodness of fit test, to test the k-specified cell probabilities denoted as pi I naught. Okay, so if you think about what pi I naught is in the context of our example, those were the numbers specified, 13 or 0.13, 0.14, and so forth. So that I want to test here, in particular, if you look at the null hypothesis, that pi 1 is equal to pi 1 naught, that pi 2 is equal to pi 2 naught, all the way up to pi k is equal to pi k naught. Okay, and the alternative is that at least one of the cell probabilities differ from the hypothesized value. Okay, what we're going to use here is this test statistic. It's called a chi-squared goodness of fit test statistic. And what it does, it basically compares what you observed, that's Ni, what you observed from your sample for that outcome, with the expected outcome, the expected number of values for that for the ith category. Let's call it a category. So, and that can be gotten by n times pi I naught. Now this is the expected number under the null hypothesis. Okay, so you look at the difference between what was observed and what was expected. You square it, divide by what was expected. You add that through all the categories there, and if you do that, then it turns out that this test statistic here has an approximate chi-square distribution with k-1 degrees of freedom for a large sample size. And a rule of thumb for large for this particular technique is that the expected cell count is 5 or is greater than 5 for all the categories. And so what we're going to do here is we're going to reject this null hypothesis if our chi-square test statistic is large, or in other words, if it exceeds some chi-squared critical value. So here's a picture of our rejection region. You can see there we would reject for large chi-squared values, fail to reject for small values. And if you wanted to compute a p-value for this kind of test, it would be given by the probability that the chi-squared exceed or is bigger than or equal to what you observed. Okay, so let's come back to this example here. We're going to actually need some data, and again, if this was a face-to-face class, we would perhaps I'd pass out many bags of M&Ms or just one large bag of M&Ms and treat that as our sample. And so I'm going to actually reference some past data from a past class where we did this particular problem here. And I'm going to have for each of the color categories, brown, yellow, red, blue, orange, and green here. Okay, and so with that past data, it turned out that we looked at a total of 601 M&Ms. I can't remember if that was several bags of M&Ms or one large bag of M&Ms. But anyway, it turns out that there were 71 brown M&Ms, 88 yellow, 78 red, 122 blue, 127 orange, 115 that were green. Okay, so that was what was observed, the observed cell counts for those respective categories. The expected cell count, how do we get that? So let's look at this first entry here, the expected value of N1. Now it's the expectation under the null hypothesis, so it's N times pi 1 naught. Alright, so under the null hypothesis, we would expect to see 601 times, what was pi 1 naught? That was 13% there. So times 0.13, under the null hypothesis, we would expect to see 78.13 brown M&Ms. Yeah, so clearly you can't You can't, well, I guess you could have a broken M&M to get 0.13, but this expected count is an average there over the population, assuming the null hypothesis is true. So we would have 78.13 here. The expected count for yellow turns out to be 601 times 0.14. If you do that, you get 84.14. That's 78.13. Then 144.24. You can do the arithmetic for each of these categories. And lastly here, 96.16 was the expected cell count for the green category. So what I can do here to test this hypothesis is I can compute my test statistic, my observed test statistic. Again, it's this chi-squared test statistic. That's the observed cell count minus the expected cell count under the null hypothesis. Then all of that divided by the expected cell count. Okay, and I'm going to sum through all the categories. So I is going to go from 1 to 6. Okay, so if I look at my first category there, my N1 was 71, and the expected count was 78.13. So I'm going to have 71 minus 78.13. I'm going to square that, divide by 78.13. And then here I'm going to go to the next category, which would be the yellow. Yellow here I've got 88, so I'm going to have 88 minus the expected count was 84.14. Okay, square that, divide by 84.14 plus dot dot dot. Okay, the last cell count was 115 minus 96.16 squared, and then over 96.16. Okay, so just looking at the data, you know, when you look at the number of counts compared to the expected count, you know, red is pretty close, yellow is kind of close, but blue and orange, well, blue is pretty far off from the expected count, and so is green. And so those may be categories that would contribute to rejecting this null hypothesis and accepting the alternative there. Okay, but let's see, let's compute the test statistic to be sure. If you compute that test statistic, you would get 8.33. 8.33. Okay, so what I want to do, a couple of ways to do this is I can compute a p-value, or I can set up my rejection region, and I'm going to appeal to the chi-square distribution. Remember, the degrees of freedom here is n-1. I've got 6 categories. I say n-1, it's k-1. So I've got 6 minus 1, or 5 degrees of freedom. If that's my degrees of freedom, my p-value here is the probability that I would see a chi-squared value bigger than or equal to 8.33. Now, if you look this up, you could use Excel, or you could use JMP or some other stat package to try to get this probability and get it exactly, or get it really close to its value. If you appeal to the book, though, and their chi-square chart, and that's what I've done, if you notice, you can look at the probability that chi-squared exceeds 9.236. So you can look at the book there, and it'll tell you that probability is 10%. Or in other words, the upper 10th percentile of the chi-square distribution with 5 degrees of freedom is 9.236. If you want a picture of that, here I've got chi-squared 0.10. Of course, the area under the curve to the right of that is 0.10, and this value is 9.236. And my test statistic 8.33 clearly lies to the left of that, and so this probability is greater than 10%. And so that would, my decision would be I would fail, because my p-value is large here, I would fail to reject H naught. Okay, so we would say in an interpretive statement that we have insufficient evidence to reject the color distribution claim by hypothesized publication. Okay, that doesn't mean that these proportions are exactly correct. It just means that we don't have enough evidence to refute that. Okay, so that is inference on several population proportions, in particular testing if several of them are equal to specified values. I do want to say that this test can be formulated that's similar to a one-way analysis of variance test for comparing several population means. I can force pi 1 naught, pi 2 naught, and pi k naught to be the same number. In particular, if it's 1 over k, then I'm testing to see if the underlying population proportions are equal to each other. Okay, and so this particular test allows for that nice question to be asked. Okay, so chi-square goodness of test on several population proportions. Next, we're going to look at contingency table analysis.